Am I audible, Ayush? Ayush, yeah, good morning. Can you hear me?
Yes, sir.
Okay. Ganesh is supposed to join today, right?
So I don't know about him, sir. I think he's returning back, sir. That's why you can
Did
join.
he join the classes in the morning?
No, sir, he did not.
Oh, acha, acha. Okay, then I won't wait for him. Okay. So today we are going to begin the second chapter. Okay, first chapter is more or less done. Only one topic is left: nuclear electric moment. That thing I will discuss later. It's a vast topic. Just see how much is required for you. Okay, and that will take some time, and I think we should accelerate our pace. So yeah, today we would be beginning with the second chapter called nuclear models. Can you see my screen?
Yes, sir.
Okay. Let's see the recording. Is it going on? Yeah, recording is going. So nuclear models. Can you tell me what is a model? What is a model in general? Yes, Ayush. What is a model?
Sir, sir, it's a figure, sir.
Figure. Okay. Okay, you can
That
say
represents
who is a
the
model. That also will work. Okay. Yeah, that represents. Okay, figure that represents something. Fine.
yes, sir.
So I went through some definitions, some standard definitions of model, and this is what I arrived. I went to dictionary.com. So model, there are many words you can use it as an adjective as well, like a model school, a model institution, or you can use it as a verb, like I model this thing, like that. So as a noun, it is what you said. It is a representation, which is generally a miniature. I have a huge thing. I'm just, in a nutshell, trying to represent that. It is already there. I am presenting it once more. And it should highlight some details like construction or appearance of something. Also, it is a standard or an example for imitation or doing some comparison. Right. So we would be taking both the things together. So in our subject, suppose I don't know any something in details. I mean, I can't take it outside. I can't touch it. I can't uh, show it elaborately, but I can guess something, or I can predict some of its behavior. Based on that, what I will do, I just try to make you know a model kind of thing, a prototype. Like in physics, we have used these kind of models before. Can you tell me which model this is? You studied it in your school days.
Sir, plum pudding model.
Yeah, very good. Plum pudding model. I think it was put forward by J.J. Thomson, that he assumed that the atomic structure is like a plum pudding or a fruit cake, where the bulk is constructed. Bulk is like an ocean of negative, sorry, positive charge. Hmm. And like nuts or fruits, negative charges have been sprinkled on it. So it may look very delicious. It looks very funny, but obviously it is not the case. Okay, because this thing drastically failed to, first of all, take care of the two things: the charge neutrality and the stability of the atom. Neutrality was taken care by saying that the total charge, negative and positive charges are equal. Still, this thing doesn't make much sense. Then came the famous Rutherford atomic model, where he did this gold foil experiment. Do you remember this experiment, Ayush?
Yes, sir.
Can you briefly tell me what does it say? What did it say? What was the experiment about? Anything that you remember?
Sir, the alpha particles were
Hmm.
made to pass through the gold foil,
Okay.
and its deviations were checked, sir.
Yes, very good.
According, according to that, sir, he proved that there were electrons and there was a large uh, nucleus at the center, sir.
Okay, very good. Can you tell me why this kind of detector screen was used? Circular kind of thing?
Sir, I don't know about it.
No, no, you can guess from the picture.
Uh, so to
Yeah, you said that alpha particles were scattered, right? They were
yes, sir.
deflected, scattered, whatever. Now
Sir,
tell me, had yes, yes,
uh, sir, to check the angles of the deviation, sir, I guess.
yeah, very good.
What?
I mean to get as much alpha particles scattered as possible. Okay, to detect as many as we can. Had we just put a screen only at the back, we would have got only those things which were very close to 180-degree deviation, isn't it?
Yes, sir.
So this kind of thing was used, and the gold foil was very thin. Can you do you remember why it was very thin? Why it was taken like that?
So that the electrons can pass through easily. Yes, sir.
Not electrons, alpha
Electrons can pass.
particles.
So alpha particles
Hmm.
can pass through
Actually,
easily.
it was taken very thin so that it is only a single layer of atoms. Okay, so that the gold foil was comprised of only one layer of atoms. Okay, like only one layer was there.
Yes, sir.
Hmm. So the alpha particle could interact with one layer only, because multiple layers would, take care of that attenuation thing. That is when alpha particle strength would go on decreasing. Hmm. So it was attempted to take as thin as possible. Okay. So you said that he could. By the way, why was this experiment done? Why was it done? What was the motive behind it?
So to prove the model, sir, that he
Yeah,
postulated.
to know the atomic structure.
Yes, sir.
So what he found that most of the alpha particles hit the screen straight. That is, it went almost undeviated. So from there, he concluded that most of the atom is vacant. Hmm. Very some number of particles were deflected, and the deflection was taken care by the fact that by the angles it was concluded that there might have been some negative charges around, and very few in number, like one in a million, alpha particles would go deviated back to the source. That is, it would have a head-on collision, right?
Yes, sir.
So from there, it was concluded that a very small region of the atom has a very concrete positive charge concentrated. Why positive charge? Because the deflection was in the opposite direction. It was as if a ball was hitting a wall, and very less number of alpha particles would deflect that way. So it was concluded that a very small fraction of the atom has positive charge, and then the model was made, isn't it? That it is the nucleus. Okay, so this model is very close to that solar energy. Sorry, solar system model of planets, isn't it? So this is also one model that we learned in school. I'm not taking care of all those models which we used to see in our biology classes. Like those are just imitation model of circular system. Okay, lungs, not those things. I am talking about these models. They are called teaching aids, which school teachers use. And the next model was Bohr's atomic model. So what did this model tell us? Anything you remember here? Ayush, what do you remember from this model?
Sir, sir, it was the same as for the fourth model,
Hmm?
but the cells were divided as K, L, M, and L, sir.
Okay, yeah, very good. And it told us about the condition of an electron to stay in an orbit, and also about some discrete properties they possess, like angular momentum, isn't it?
Yes, sir.
So we are very much acquainted with models, and model always does not mean that it has to be a picture or a diagram or structure. Okay, it can also be collection of postulates, some mathematical equation. So we are very much okay with models. Now, what is a nuclear model? So over the years, people did many experiments, and they eventually, reached a consensus with the structure of the atom. If you go by history, then you will see that first the electron was discovered, hmm, then the nucleons. That is, the more we wanted to go inside the atom, we required more energy. We required higher energetic particles to probe them. That's why we had to wait for some years. Hmm. First electrons were discovered. And then people did many experiments, and they were okay with the structure of atom. But the nucleus had some peculiarities, and to address these diverse features, or what should I say, diverse types of behavior of a nucleus, the scientists they use many theoretical description, because as I said that it's not possible on many occasions to just take something in your hand and just look into that. One instance is the nucleus. Hmm. So what they did, they used many analogies. They tried to correlate different things, and they saw that how the resultant collection predicts with the real life examples. So this is what we call a nuclear model. Got it? So you observe different properties of nucleus. You try to look for the probable cause behind this, behind that. Then you keep those things in, arrange them in logical manner. Then you get a model. Clear?
Yes, sir.
Okay. This is also a very sanguine definition from Britannica.com. So now, what are the questions exactly that we are talking about? These things. Hmm. Function of atomic nuclei, description. What are the questions? There are many questions. Hmm. The first one is that if you remember this graph, the packing fraction graph, binding energy per nucleon versus the nucleon number. Hmm. So what we saw that the binding energy per nucleon went on increasing in the low atomic number range. Then it reached a peak at 8.8 milli mega electron volt for iron. After that, more or less, the value was constant. So if I only take care of this region, if I just separate out this region, we can say that it is almost constant, isn't it? There's a very slight decrease in the value. Can you notice it from the graph?
Yes, sir.
Like this kind of graph we had for transistor characteristics for which mode? Yeah, for C mode. I don't know if you remember the graph or not. The output characteristics curve, it was slightly like this, slight increase, not totally constant like CB mode, but yeah, we could have taken that as constant. So why is this thing? I mean, people are very peculiar. They always want stability, but once when they get something very stable, very utopian, they ask question. So this was one question: why is this thing happening? Second was, why the nuclei? Those are magic number. Remember what are the magic numbers? Do you remember it?
No, sir.
Okay, I told you you must remember the values. These values: 2, 8, 20, 28, 50, 82, 126. I mean, how many? 1, 2, 3, 4, 5, 6, 7 values. So it is observed that if the number of nucleons in any nuclei is any of these values, okay, any of this magic number values, then that nuclei will be exceptionally stable. You can see this graph, this kind of graph I don't think we have used very often. It is a 3D graph. If you remember that our first webinar which we hosted in September, Dr. Bakchi, he gave a presentation. There also he showed a 3D graph. Hmm. So it is nothing. We use x and y axis. So you can call this the z axis in this case. So here we are plotting the binding energy. Hmm. And along this direction, that direction we are plotting the proton number. This direction plotting the neutron number. So you can see the boxes here. I mean the base of the box that depends on the number of neutron and proton, like this. Suppose number of neutron is 2, so this will be 2. Number of proton is say 1, so this would be 1. So this is what we get. Okay, now along z axis what we have the binding energy. Suppose binding energy is 5 millivolt, sorry, million electron volt. So this altitude is 5. So what we will get? We will get blocks like this. Are you getting the graph?
Yes, sir.
Clear, or should I repeat?
Sir, just repeating in brief, sir.
Okay. I require help from some by some what should I say? Yeah, shapes. So I have three directions. Along this direction, I am plotting the binding energy. And what I said, magic numbers mean that either your proton or neutron, that is the nuclear number, should be like that 2, 8, 20, whatever. So this way I am plotting the number of protons, and this way I am plotting the number of neutrons. Are you okay with the direction? Proton, neutron, binding energy.
Yes, sir.
Now suppose I have a instance where the proton number is 2. Suppose this is 2, and the, yeah, this is, suppose this much is 2, and the neutron number is something, say 4. So this is 2, this is 2. Suppose it is 4. So this much is what? 4. This much is 2. Let me increase it a little bit. Yeah. So this is 4. This is 2. Got it?
Yes,
Did you get
sir.
it?
Yes, sir. Yes.
Fine. So that is why we are getting, see, these rectangular shape. Now what about the three-dimensional thing? Now suppose this nuclei has a binding energy of 5 MeV. So where will I plot the binding energy? Which direction? This way. Suppose this much is 5. So what I will do, I will draw, I will connect everything like this, because this entire thing represents 5 MeV. That's why I would be drawing a drawing perpendiculars like this. Same thing that we used to draw for Cartesian coordinate. Whenever we want to join the point, what we do, we just draw perpendicular. I mean, whenever we want to show the coordinates, abscissa and ordinate. Okay, so this much is suppose say 5 MeV, million electron volt. This much is suppose number of neutrons, n equal to say 4, and this much is number of protons, p equal to say, just a minute, p equals say 2. Got it? We are not drawing a 2D graph like say this is a is 4, this is 5. So what we do usually, we join it like this, isn't it? Then we write the coordinate
Yes.
here x comma y. Here we are having a 3D graph. Are you okay with the graph now?
Yes, sir.
Because it depends on how many variables your function is depending on. So you can see we have a number of proton and neutron equal to 2, that is for helium. 8 is for oxygen, 16, O 16 8. 20 is for calcium, 40 20. Uh, then for nickel we have 28. Hmm. So it is seen that you can see there are certain peaks. Like in this region, these are all dwarfs. Okay, suddenly there is a peak, and when you look investigate into its internal constitution, you will see it has 82 number of protons or neutrons. Protons, in fact, in this case. Got it?
Yes, sir.
Yeah. So this was also the question: why are these things having so? I mean, these nuclei are so stable. Higher stability means higher binding fraction or binding energy. Okay, I won't record this one. Delete this graph. Yeah. Third question was that, like atoms or electrons in atoms, to begin from the beginning, it is observed that nucleus also can go to a higher energy level called the excited state. Hmm. And it is always expected to be in the ground state. I mean, when everything is normal, it is expected to be in the ground state. Like the same thing which was predicted by Bohr's theory. And this thing is totally quantum mechanical, isn't it? So why this thing happens for nucleus as well? Got it? Was the third question.
Yes, sir.
And the last one was, it is observed that some nuclei like say uranium 92, I think 238 atomic number, sorry, mass number. Hmm. Some nuclei are alpha emitters by default and some are beta emitters. I think you understand what alpha beta emission means. You know little bit,
Sir.
isn't it?
Yes, sir.
We also know that these things are related to radioactivity, which is a nuclear phenomena. Radioactivity has nothing to do with the outermost electrons. And whenever we have something to do with outermost electrons only, we call that a chemical phenomena. So if that is a nuclear phenomena, that means if everything happens in the nucleus, then how come alpha and beta particles are coming out from it? because we know inside the nucleus we neither have alpha nor we have beta emitters, is not it?
Yes, sir.
Like, had this been emission of nucleon, neutron or proton, if it was possible at all, then that would have been a plausible thing there inside. But how these things are happening? So all these diverse questions, some of them are related to each other, some are totally unrelated. These led scientists to make some postulates, some analogies, and based on that, we have something called nuclear model models, in fact. So these are the famous models. I think in our syllabus we would be studying only the first two in details: liquid drop model, shell model, collective model, optical model. Hmm. Now you can ask that, sir, why we have so many models? The thing is that none of them is has been able to explain all the properties of a nucleus completely. Okay, like if we go by that wave particle duality, what do we say that some properties of light can be explained by its wave nature, some by its particle nature. But what we say, the two nature are complementary to each other, and none of the nature can explain fully light, isn't it? So likewise here we have some models. So the first one is a very simplistic one. It is the liquid drop model. Do you have any knowledge about this? Have you read it before?
Sir, in third semester we studied.
Okay, what do you remember? Anything from this?
Oh, not third semester, sorry, fourth semester, sir.
Acha, acha, okay.
Fourth or fifth, sir.
I think fourth semester, maybe.
Yes,
I didn't teach this paper, so I don't remember. Back then, I was not there with that paper.
yes, sir.
Anyway.
Siddharth sir taught us.
Oh, Siddharth sir. Then that would be your third sem, modern physics, little bit.
Yes, sir.
Okay, so what are the assumptions of this model? See, what I said, that a model has different components. That is some assumption or some, logical reasons. So this model has some assumptions which we can easily, relate with our daily life. As the name suggests, it tried to draw analogy between a liquid drop and a atomic nucleus. So the first assumption was that, and the assumptions were made keeping in mind the ground reality as much as possible. So they said that the nuclei of all elements, they behave like a liquid drop, not any type of liquid, that of a incompressible liquid. That is, simply we can say that a liquid which whose density doesn't change with application of pressure. Okay, and that density is very high. Got it? What is the first assumption? That nuclei is like a liquid drop of a very of an incompressible liquid of very high density. Fine.
Sir,
Can you tell me why we are choosing very high density? Any
sir,
idea?
I think because of the nucleus, nuclear forces.
Did we calculate the nuclear density before in any class? Did we calculate the nuclear density and found its value?
So I don't remember it.
Then you were absent in that class, maybe,
Yes,
because
sir.
we have already calculated nuclear density, and it was found to be 10 to the power 18, so 16 times more than that of water. 18 times, I think. So
Yes, sir.
nuclear density is nuclear matter is highly dense. I mean, absurdly high. That's why the assumption is made of a liquid. And also we saw that the nuclear density does not depend on the atomic number, mass number A. That's why this assumption has been made. Second one is that under the equilibrium of forces acting inside the nucleus, it is seen that the nuclei remains spherically symmetric under the action of strong attractive forces. See, you have to understand one thing. Whenever there is an internal pull towards a point, that is attraction, then the tendency of the system is to become a sphere, isn't it?
Yes, sir.
When there is a equal, I mean, when there are equally attractive force vectors towards a point, they are all equal in magnitude, then we assume that it should be spherical. The same thing happens with a liquid, and which is due to something called surface tension. I think we remember this as well.
Yes, sir.
Everything, why bubbles are spherical, those things, why when a soft film was made, it had a tensile force. Third one, as I already said, that it is seen that nuclear density is independent of its size. That is, it doesn't depend on the size of the nucleus. That is, a nucleus of hydrogen and a nucleus of uranium, though they are very I mean diverse in size, the nucleus will have same density. Same is with a liquid. Provided it is an incompressible liquid, the density of a liquid does not depend on its size. Like, see, liquids doesn't have size, they have volume. So if I have 1 liter of water at 4 degree Celsius and you have 1 gallon of water at 4 degrees Celsius, obviously the density of water in both cases is what? 1 gram per cc at the temperature, isn't it?
Yes, sir.
So that's also a plausible thing to assume. Number four would be that the nucleons, they move in a spherical enclosure. We'll see this when we study nuclear forces. That is, they are nucleons inside the nucleus. They are bounded. I mean, they are allowed to move only in a potential barrier. That means potential barrier. I think you have studied this thing, right? Potential barrier, barrier potential.
Yes, sir. Battery
Pot-
potential.
yeah, actually, that is different. Barrier potential and potential barrier are different. Uh, have you studied that thing? One-dimensional potential. Well,
Yes, sir. Last time we studied it.
last sem step potential. So what is the barrier? In fact, barrier is that the boundary from where potential becomes infinite. Once potential is infinite, that means the particle inside has to cross that infinitely large barrier. So we safely say that it is the boundary beyond which it cannot go. So inside the nucleus, the nucleons also have some kind of restriction like that. And this same thing is with molecules in a liquid. Same thing, that in a drop of liquid, the molecules can move anywhere but inside the liquid. And the third one is this graph only, that the packing fraction, sorry, binding fraction is more or less constant. Likewise, the latent heat of vaporization of a liquid is also constant, isn't it?
Yes, sir.
So you can see, yeah, these things look very, I mean, oversimplistic, but yeah, you cannot say these are incorrect. So these were the assumptions made in the nuclear liquid drop model. So now the model has to be built on these assumptions. At the end, we want an expression of binding energy. So one by one, we will do some approximation and we'll be getting some terms to the binding energy. Okay. So what is the first assumption? The first assumption is like that. Just look into this picture. Don't go by the colors, just go by the equal shape. So it is assumed that the nucleons in the nucleus, they are like this. They are tightly bound with each other inside the nucleus, which gives the nucleus a spherical shape. Okay, they are tightly bound so that the volume of the nucleus is minimum. Fine. Is it okay?
Yes, sir, it's okay, sir.
Fine. So when we speak of nucleon, that means proton and neutron. Now they will be in pair because they are bonded, they are bounded together. So pair can be proton proton, proton neutron, neutron neutron. So simply we are calling it nucleon nucleon bond. Fine. So each bond is associated with some energy. Remember this one. Each bond has some energy with it.
Yes, sir.
In chemistry we learned it. That's why we need to give something from outside to break the energy, as to break the bond. So let us assume that the you can call this epsilon or E, whatever. So for each nucleon nucleon bond, that is for each pair, we have an energy associated equal to now in one pair, that is in one bond, there are two nucleons. So we can say that each nucleon has a binding energy of half E. See if you can understand this or not.
Yes, sir. Can you explain it again? That the binding energy.
For each pair, for two nucleons, there is a bond, and the energy associated with the bond is E. Now in each bond, there are two nucleons. So if two nucleons account for an energy E, then for one nucleon, it should be half of E.
Yes, yes, sir.
Okay. Now let us visualize it like this. It is very tightly packed, and this tight arrangement leads to the minimum overall volume. Obviously, the minimum volume should be spherical, and that volume should be the least possible one. Now let us assume that each nucleon has n other nucleons in its contact. Okay, just think yourself. You are in a overcrowded bus, and there are 100 people apart from you. Fine. It's a bit hard
Yes,
to
sir.
visualize because we are not spherical. So here it is assumed that each nucleon has contact with n other sphere. That n needs not to be 100. Okay, n can be anything. It depends on the structure. N can be 4, n can be 8. It depends on whether, I mean, how the arrangement is being made. Like you are in a bus, and it's like you're always in contact with, physically in contact with four people. One to your left, other to your right, one to your front, other on your back. Got it?
Yes, sir.
So it is assumed that all the nucleons have exactly four or say n number of other spheres in contact with each other. I think you are getting the picture.
Yes, sir.
And since they are closely bound, that's why we can say, yeah, everyone has this n number of spheres. Now we know that each nucleon has an energy of half this one, half epsilon for one nucleon. Now one nucleon is in contact with n other nucleons. So what would be the binding energy for it? N times half epsilon. When you are in contact with four people, with each people you are making a bond. Okay,
Yes.
so alone you had an energy of half epsilon. Now you have four more people. Then how many bonds you will make? Four more bonds. That is 4 into half epsilon.
Yes, sir.
That is, here 4 is taken as n. Now
Yes, sir.
that is for only you. You are the only passenger, one passenger. Suppose the bus has a number of passengers. That is, the nucleus has a nucleons. Simply multiply this by a.
Yes, sir. Understood.
So this thing is very simple, and like this came an energy term which is responsible due to the volume of the nucleus. So this thing is called the volume energy term, or volume energy simply. That is, EV is equals to NA by 2 times epsilon. Now see, apart from A, remaining terms we can take as constant. I mean, the value can be calculated. The value is supplied most of the times. So that constant is taken as A1. So you can see volume energy is simply A1 A. Got it? And if you are still in doubt
Yes,
why
sir.
we call this thing as volume, so if the nucleus is spherical, you know that sphere has a volume of 4/3 pi r cube. And assuming the nucleus as a spherical thing, we know that r is written as r equals to r naught a to the power 1/3. Remember
Yes,
this
sir.
formula? Yeah.
Radius of the
So
nucleus.
very good. Radius of the nucleus. Just take cube. This thing is constant 1.2 for me approximately. So you can see the volume is proportional to A. So we can say that the A here, it represents the volume of the nucleus, and it is related with the energy like this. Got it?
Yes, sir.
So this term came because of the arrangement inside the volume. Now tell me one thing, that suppose take let us take the consideration of the bus. Now obviously the bus is not infinite, or you are in a metro or a passenger train, whatever. So is it possible that for all the passengers, no matter how closely they are packed, they will be in contact with four people always? Is it possible all the time?
No, sir.
Where does it seem impossible?
Sir, when the passenger moves.
No, let us assume that they are not moving, or if they are moving, then no, let us assume that you all are frozen. I've taken a picture, suppose. Hmm. Or if you are moving, then also same thing happens. Think by the position of all the passengers.
So the passenger, outer part passenger, sir. The
Yeah,
outer
yeah, you're coming
nucleus.
closer. Outer means
The
which
surface
passengers?
nucleus.
Very good. The passengers who are at the wall, next to the wall,
Yes, sir. Yes, sir.
right? Same thing. You remember it was there in that ideal gas model, isn't it? That is,
Yes,
if
sir.
someone is inside the bulk, that is possible. But what about the things that are at the surface? The passenger who is in the just next to the wall, he can be in contact with three other people, but one people not, because no one is outside the train, and if someone is outside the train, he won't be in contact with that person. So here also, suppose, okay, everything is fine, we have a spherical nucleus, but the yellow colored nucleon will experience force from, say, one, say it is experiencing a force from 1, 2, 3, 4 other nucleons, but someone in the middle or at the bulk will experience even more force, isn't it?
Yes, sir.
Very simple thing. So what the volume said, that everything looks very, utopian here, very simple. I mean, very democratic. Everyone is equally getting the opportunity for experiencing this energy. But no, what about the people who are at the corner? So now, what scientists said that yes, some correction, not correction, I mean some energy will come due to this surface factor, and that should be subtracted from the volume factor. I think you got the reason why we should subtract it,
Yes, sir.
because we were taking that in excess. Hmm. So this term we'll call it the surface energy term. Hmm. Let us see what it is actually. Now the surface energy term, like volume energy term, is dependent on the surface area. Obviously, if you have a larger surface, these factors will be more effective. So surface of a sphere is 4 pi r square and r is this. So this term should be proportional to a to the power 2/3. Okay.
Yes, sir.
And the constant parts, if we take that as a2, so this energy term would be minus of this one. Minus is only because of that thing, that all the atoms, all the nucleons are not experiencing the same force. Okay. And these values are, I mean, this effect is more pronounced for lighter nuclei. The third one we will discuss it tomorrow. So the third one is due to the uh, electrostatic force. Can you tell me what kind of electrostatic force are there inside the nucleus?
Sir, the nuclear forces and with yes, sir.
No, no. Apart from nuclear force, electrostatic force means what? Attraction or repulsion due to charges.
So attraction,
Is
sir.
yeah, attraction of what?
So
Between
positive
what?
and negative, positive and negative charges.
Where is there any negative charge inside the nucleus?
No, sir.
That
Mm.
what kind of force will be there due to charges?
So repulsion, sir.
Repulsion due to protons, right?
Protons. Yes, sir.
And the attractive force that you're talking about, that thing has to be taken care in the nuclear force domain, because we can't explain it like this. It's not a magnet, that a magnet can attract another magnet or a magnetic material which is not a magnet all the time. It's not like that, that a proton will attract a neutron. So it's also true that the repulsion will always, try to make the nucleus unstable. That is what repulsion does, isn't it? Repulsion always tries to, break the stability. You will never find any system which has been stabilized by repulsion alone. Hmm. Whenever there is repulsion, we just call for an attraction to take care of that. Even attraction also doesn't take care of stability alone. If only there is attraction, then the thing will collapse. Anyways, so the repulsion between each proton pair, that is between two protons at each instant, it will always try to decrease the binding energy. Okay.
Yes, sir.
So tomorrow we'll just try to see what is, hence see, when something is decreasing, then we need to decrease something out of this one as well. It's like winning a huge amount of money in a reality show or something. Apparently you want this amount of money, but you saw that first you have to pay some tax, like the surplus term, then you have to pay something to the sponsors, which is this term. So again, this term will cause some decrease in the overall binding energy. Okay.
Yes, sir.
So we'll discuss it tomorrow. Fine.
Thank you, sir. Yes, sir.
If you have any doubt, you can ask. Any doubt, anything.
Uh, no, sir. No doubt.
Which book you are following for this one?
Sir, Chattopadhyay and Rakshit.
Acha, acha. The sir is following that book. I mean, did he recommend anything?
He's using Bigo, sir, I guess.
Bigos, no, Bigos is for electronics.
Oh, not Bigos.
No, I
No,
don't
sir,
think
he's
Bigos.
using another book, not
Church.
Roxy, sir.
If see these things are there in any book, you can follow that and make your notes on your own. That is the bigger concern. Okay. Okay, then let's meet tomorrow. Take care.
Yes, sir, thank you, sir.